This video is from my Algebra 1 class and is over Lesson 33, Finding the Probability of Independent and Dependent Events. So ladies and gentlemen, I've got a few things here. You might want to pause the video once I get down kind of to the end of the explanation of the definitions and finish copying the rest of it. So here we go. Independent events are events where the likelihood of one event does not depend on the outcomes of any other events. And so I would point out here that the prefix in means not. It does not depend. So independent events would be like the probability of flipping a coin and the probability of it raining today. Well, the outcome of flipping the coin has absolutely no effect on whether or not it will rain today. Those are completely separate. Or something a little less extreme, looking at the probability of rolling a die and getting a certain value versus flipping a coin and getting either heads or tails. Your die roll has no effect on your coin flip. For that matter, if we even think about board games also often come with two dice. When you roll one die and you roll another die, what you roll on one die has absolutely no effect on what you roll on the other. And so their likelihoods, their probabilities are not affected by the outcomes of each other. Dependent events, however, have one event that does depend on the outcomes of the others. So depending on what happens in one event, it can affect the probability of the following event. As a reminder, remember that if we write something along these lines, this is the probability of A. This is not a multiplication problem, even though it looks like it. This is more what we would consider function notation, which we talked about a few lessons ago. So we're finding the probability of whatever is stuck between the parentheses. So in probability, A is often listed just as kind of the generic event. So just like X is kind of our standard variable, A is our standard event. It stands for something that happened. So ladies and gentlemen, when it comes to independent and dependent events, we have a formula for each of them for how to find their combined probability. So for independent events, since whatever happens with A has absolutely no effect on B, first of all, we need to understand when we say and here, we do kind of actually mean then. So A, then B. Sometimes they can happen together, but it's more helpful to think of it as this one and that one, this one, then that one. So often it'll be more of a then. But if they have absolutely no effect on each other, then we're going to take the probability of A all by itself. We'll take the probability of B all by itself. And to find the combined probability of both of them, we multiply. So for independent events, the probability of A and B equals the probability of A times the probability of B. For dependent events, this one's a little trickier. So again, we think of this and as a little bit more of a then. So A happens and then B follows after it. It starts off the same. We're still going to find the probability of A. So assuming A is the first event, the thing that would chronologically happen first, well then, that's just going to be plain old probability of A. There's nothing that happened before it to affect its probabilities. And we are going to multiply again, but it's not just with the probability of A, or excuse me, probability of B. It's the probability of B given A. So in other words, what's the probability of B given that A has already happened? And so we'll take a look at some examples of that here in just a moment. So before we get there though, let's go ahead and pull out a highlighter. So independent, and just for good measure, let's just go over the word itself there. Match that up, and then I'm going to choose a different color. So this time, I'm going to grab my purple. I don't use my purple very often. Blue and purple kind of look nice together. Oops, went a little too far there. All right, so let's try a few of these out. So first of all, if I were to show you something that looked like this, typically in probability, if we have a capital H, it usually means heads. We're usually talking about flipping a coin. So what is the probability here of flipping a coin 2 times and both of them being heads? Well, first of all, does one coin flip have an effect on the other? No, it doesn't. So since it doesn't have any effect, these are independent events. So therefore, this is just going to be the probability of getting that first heads times the probability of getting heads again. Well, the probability of getting heads is 1/2. It's one option out of 2. The probability of getting heads, well, it's the same thing. So therefore, the probability of getting double heads is 1/4. If I were to give you something like this, you might assume with a 3 and a 6, this kind of seems like maybe this has to do with a die roll, where I get a 3 on one die and a 6 on another. Well, what I do on one die, does that affect the outcome of the other? So if I get a 5 on one die, does that make it more or less likely that I'll get some other numbers on the other die? No, it's completely independent. They do not depend on each other. So then this is going to be real simple, because it's just going to be the probability of getting a 3 on a die times the probability of getting a 6 on a die. So the probability of getting a 3 on one die and a 6 on another die, well, probability of 3 is 1/6. Probability of 6 is 1/6. So the combined probability is a 1/36. So now for the sake of example, let's say we had a bag of marbles. And in our bag of marbles, we have 3 green, 4 blue, and 5 red. And we're going to pull 2 marbles out of the bag. And first we're going to do it with replacement. So replacement is just a way of saying we're going to put back what we pulled out before we take out the next one. So I'm going to pull out a marble, replace it, so put it back in the bag, pull out another marble. Well, if you put your marble back before pulling out the next one, then you have the same exact mix of marbles as you had at the beginning. So in this case, if I asked you what is the probability of pulling 2 greens, so pulling a green followed by another green, with replacement, this would be independent events. And so we'd be looking then just at the probability of getting a green, so that green, times the probability of getting green again. Well, if we take a look at our greens, 3 plus 4 plus 5 is 12. So green, there are 3 greens out of 12 total. Well, that's 1/4. We have a 1/4 probability of getting a green times a 1/4 probability of getting a green as long as I put back what I took the first time. So a combined probability of 1/16. You have a 1/16 chance that if I pull a marble out, put it back, pull out another marble, they will both be green. On the other hand, what if we now do it without replacement? So when I pull my marble out, I'm going to keep it out. So then the probability of pulling a green and a green, well, now this time if I pull one marble out, I no longer have 12 total in the bag. That is going to change the probabilities of the rest of my marbles. And so this becomes a dependent event. A dependent event. So in this case, we're going to have the probability of pulling that first green, but then for the second one, it's going to be the probability of pulling a green given we've already pulled a green. So for this, we may want to think through the sample space. So for this first probability of pulling a green, we have 3 greens, 4 blues, and 5 reds. So the probability of pulling that first green, there are 3 out of the 12 total. So that's a 1/4. For this one here, though, if we've already pulled a green, so given that a green has already been pulled, then that means that we'll only have 2 greens left in the bag, but there'll still be 4 blues and 5 reds. So this is sometimes called conditional probability. This conditional probability, or the dependent probability here, this depends on what you pulled the first time. So assuming we pulled a green the first time, now there are only 2 out of the 11 total that are green. So my second probability becomes 2/11. Well, a little reducing before multiplying. And then if I multiply this up, the combined probability is 1/22. So if we replace the green marble, we have a 1/16 chance of getting 2 greens. If we do not replace the marble, we only have a 1/22 chance of getting 2 greens. And that's dependent probability. So let's say we're looking at pulling 2 cards from a deck without replacement. So first of all, if you pull a card out of a deck, there are 52 cards in the deck. There are 4 suits in each suit. We have a king, queen, jack, and then it counts down 10, 9, 8, 7, 6, 5, 4, 3, 2, but we don't have a 1, but kind of like a 1 is the ace. And the ace can be funny. Sometimes it's a 1 in one game, sometimes it's almost like a something above the king in other games. So it all depends. But still, as far as counting goes, it kind of takes the place of a 1. So if we pull 1 card out and don't put it back, though, we no longer have 52 cards total. And so, since we're not replacing that, again, we have a dependent event. So if I asked you to find for me the probability of pulling 2 spades, so this then is going to be the probability of pulling your first spade times your probability of pulling a spade given that you've already pulled a spade. So, well, spades are 1 suit out of 4. So therefore, all of the spades make up 1/4 of the deck. So the probability of pulling your first spade is 1/4. Now after that, though, there are 13 cards that are spades. So after that, we have only 12 cards that are still spades. And instead of out of 52 total, now we've only got 51 since we've pulled 1 card away. Again, a little reducing before multiplying. Obviously 4 and 12 reduce down to 1 and 3. And then 3 and 15 we can reduce as well to 1 and 17. And so the probability of pulling 2 spades is 1/17. So how about the probability then of pulling 2 aces? So likewise, this is dependent, so it's going to be the probability of the first ace times the probability of a second ace given we've already pulled an ace. So each suit has an ace. It's one of the 13 cards in the suit. So therefore, 1/13 of the deck is made up of aces. So the probability of pulling your first ace is 1/13. Now, really there are 4 aces. So if we've already pulled one out, then there are only 3 aces left. And then instead of 52 cards total, we pulled one out, so out of 51 cards total. Again, reduce before multiplying. 3 and 51 can reduce to 1 and 17. And if we multiply this together, 1 times 1 is 1. And then if we figure out, okay, 13 times 17 comes out as 221. So it's actually far more likely that you'll pull 2 spades than pull 2 aces. And ladies and gentlemen, that is probability. Now we're going to flip to the back though, because we do have one last concept, and it's not in the title, but it is in the lesson. And this last concept is what's called odds. We began learning about odds back in pre-algebra a little bit, and we're going to push it a little further today. So odds are the ratio of favorable to unfavorable outcomes. And that is a vocab term, so let's go ahead and highlight that. Now, something to point out here is if we know our probabilities, if you take the number of favorable outcomes and add the number of unfavorable outcomes, this will always equal the number of possible outcomes. So I'm going to use F for favorable, U for unfavorable, and P for possible. So if I asked you for the probability of an event, this would be F over P. The favorable number of favorable events, or excuse me, outcomes over the number of possible outcomes. On the other hand, if I asked you for the complement of this, the complement of this would be the probability of not A. And so then this would be the unfavorable over the possible. When it comes to odds, odds are favorable to unfavorable. So the odds for A are going to be the favorable, and then we typically write odds with a colon. So the favorable to the unfavorable. And ladies and gentlemen, this is where we're adding on something new this year, because not only can we have odds for something, or odds of something, we can actually also have the odds against something. And so in this case, favorable and unfavorable actually switch places, and it becomes the unfavorable first, followed by the favorable. So the odds against A would just start with the unfavorable. So if I asked you for the odds for flipping a coin and getting heads, well, there's one favorable outcome, heads, compared to one unfavorable outcome, tails. So the odds for heads is 1 to 1. The odds for, or excuse me, not odds for, odds against H then would start with the unfavorable, 1, tails, and then finish with the favorable, 1, heads. So that's not terribly interesting. The odds for and the odds against heads are the same, which goes with their probability of being 1/2. How about what are the odds, though, for rolling a die and getting a 4? Well, there's one favorable outcome, getting a 4, to 5 unfavorable outcomes. In other words, getting a 1, 2, 3, 5, or 6. So if you know the odds for 4, you should know the odds against 4. It's just going to be 5 to 1. If we think to the front of the page here, the odds for 2 spades. Remember, ladies and gentlemen, the probability was 1/17. So 1 is the favorable number. 17, being probability, is the possible. So 1 plus what is 17? Well, 1 plus 16. So the odds for 2 spades is 1/16. And again, we pulled that from the probability of 2 spades was 1/17, which we know is the favorable over the possible. So my favorable was 1, possible was 17, so therefore unfavorable must be 16. Once we have that, it should be pretty easy to find the odds against 2 spades. Just start with the unfavorable, end with the favorable. So 16 to 1 against them being spades. And so what that means is for every 16 times we don't get 2 spades, we can expect there to be about 1 time we do get double spades. And that, ladies and gentlemen, is the end of our lesson.